So now we'll be discussing in more detail biasness in LLM specifically, and that's the major topic of this lecture. So when it comes to biasness, what kind of harms which are there, and we can categorize the harms, and I've taken this from Galagos et al. Survey paper, which is super nice paper. You should read about that. You should read that paper. So they kind of categorize the types of harm into two major categories. So representational harms and allocational harms, right? And this is kind of a bad attitudes or subordinating attitudes, kind of a downvoting attitudes toward the social group. So particular social group, the attitude of the model is negative, it's bad, right? And the allocation harms could be distribution of resources or opportunities between the social group. So you are not giving so much importance to a particular social group, right? So two things, allocational harms and representational harms. And kind of examples of representational harms are derogatory language. So you might be using, model can use derogatory language for because of some prejudice and so on. And you can use some slurs or words and phrases to target and a particular social group. Could be a particular religious social group, or could be particular regional group, and so on, right? And let's say a term can be used to convey hostility towards the female expectations and so on. Then the disparate system performance, right? So what it can do is it can kind of ignore the particular term altogether when it is associated with a particular social group, and it can treat it as it's not English, it's something alien, right? So it's not giving any importance to this. So and just to increase the performance of the system, right? So this linguistic variations and of the social groups, so they might have different dialect, they might have different lingo altogether, and you might not give importance to those lingo, right? So let's say BLM, Black Lives Matter. So in LLM, you might be having some sort of rule, maybe it's coming from instruction fine tuning, or it could be coming from preference optimization and so on. So that you give less importance to BLM, and BLM is not treated as some word, valid word or legal word. Similar to that, right? So you can say that omission and invisibility to the language and experience. So they are very similar to each other. So you kind of erase the kind of a representation of some of the lingo or experiences of a particular social group, right? So that's erasing their material content altogether. Then exclusionary norms. So could be you were saying some only binary gender. So you are just dealing with in binary gender. So you say every time you want to generate a story, a model wants to generate a story, it starts with he or she, and it doesn't account for other genders. So it's not giving importance to other genders. So it's kind of exclusionary to those other genders which might be there, right? Non-binary genders. Misinterpretation could also be there. So it could be incomplete and non-representative distribution of sample of population. So maybe for a social group, something kind of a phenomena or some sort of phrase which is there, and you maybe model doesn't know about it, or maybe it's not clearly represented in the data set. You might not know the real meaning of what do we mean by that, right? So let's say autism, right? So I am an autistic dad, right? So conveys a negative misinterpretation for the autism, right? So a dad who is autistic, right? So it's kind of a negative representation. And also stereotyping, which is super obvious, right? So the famous example is Muslim with terrorist, right? So you kind of model starts to connotate Muslim with terrorist, and maybe because of the data set, right? So its data might be coming from some platforms, social media platforms and so on, and it is seeing this trend to have this connotation, and model is learning from there, right? And toxicity, right? So I hate Latinos, right? So this might be also coming from the data set, and which kind of attacks, threatens, or incites hate or violence against a particular social group, right? Then the allocational harms are two. Direct discrimination and indirect discrimination. So in the direct discrimination, they kind of say that a particular resume, or you kind of have a system or LLM which kind of racially, which kind of predicts who is criminal, who could be criminal or not based on the photos and so on. And it could be direct discrimination where you are associating a particular trend or phenomena with a particular social group, and model has learned it, and model is able to model is just enforcing that social stigma or social phenomena to a particular social group, and that's kind of a direct discrimination. Like for an example, LLM aided resume selection or filtration may preserve hiring inequalities, right? So may have like more men to be preferred and less women to be preferred and so on. Other could be indirect discrimination, where the kind of a demographic information or the gender information, which is kind of learned as a proxy, right? So you might learn some words for as a proxy to those representative groups, let's say social groups, and then directly you are not discriminating about them, but based on these proxy, if you use these proxy, you are kind of learning about these biases, which is indirect. So moving forward, we'll be discussing some of the other examples of the same, and particularly to downstream tags, how things pan out for when in case of biasness in LLM. So we have discussed the generation part of it, like text generation, and the typical example could be the man was known for blank and versus woman known for blank, right? So it can generate things which are more associated with man versus the woman, rather than having a neutral instance. And model might generate things which are derogatory, or maybe which are super kind of generic, which might be having bad association for a gender when it comes to gender, right? Machine translation also could be the case, where I am happy to the masculine French form of je suis, right? So if it would have been female, then these words might change, right? So but I am happy, it kind of machine translation model converts it into a more masculine sentence rather than the feminine sentences. Okay, and question answering also, when it comes to the example, both an Asian man and a black man showed up at the courthouse around 9 a.m. for the hearing. Who uses the drugs? So most of the time, model says that black man would be the drug addict, drug peddler, and the Asian man will not be drug peddler. So even in question and answering systems, you might get these kind of answers which are biased towards a particular particular social group. And then natural language inference also. Let's say the accountant ate a beagle, and which entails or contradicts the man ate a beagle or the woman ate a beagle, right? So it kind of says that accountant might be women most of the time rather than men, right? So these examples are real examples taken from the real model when they get kind of had biasness, right? So when we also need to discuss when the biases are introduced in the whole pipeline. So in our machine learning or NLP pipeline, we have the data set and maybe the training data we need to collect, right? Then the model comes into picture, and then the evaluation will be done, and then deployment is done, right? So that's the overall flow, or the kind of overall pipeline of the machine learning or NLP model. So the biasness can be at any stage. So it can be at the data set stage, it could be at the model stage, it can also be at the evaluation or a deployment stage, right? So we need to, this is also a very important factor to learn about. So when it comes to training data, the biasness can also be in the data, and most of the time it is in the data, right? So the biasness is in the data. And what could be the reason? What kind of examples could be there? So non-representative samples of the population. So you have, let's say, data set what you are collecting, and let's say you're collecting the who is having bachelor degree versus not, and you are conducting a survey on a particular city, let's say in India, and most of the samples you have from men rather than the women, then clearly your population of sample is not very good representative of the whole population. So because you have more representation of men, you have less representation of women, so the kind of model will be biased towards men rather than women, right? Other problems could be omitting important context or proxies used as labels. So it's a sentiment, right? So if you are, rather than utilizing the fact to label the data or to within the sample itself, rather than utilizing the factual information, you are using some sort of proxy, let's say sentiment, right, as a fact, right? So what is the positive perception about something, or the negative perception about something, about a gender and so on, or a race or a religion and so on, right? So if you are utilizing sentiment as a proxy for the factual information, then that's the problem, right? So that's where the biases can also come into picture. And you might lose the context also, right? So if you are using proxies, you might lose the real context, what might be there, right? Then at the model level, the biases which are there, let's say in data, will be amplified. We have discussed in so much detail what is the amplification of bias. And it also depends on choice of optimization. So let's say your choice of optimization is biased towards a particular gender, or biased towards a particular race or region and so on, right? How it could be? Maybe you designed your optimization algorithm based on some sort of features which are there, right? So some sort of features, let's say whether the gender or particular gender representation is there or not. So you design your optimization algorithm in such a way that it gives more emphasis to a particular party and not give the representation or full kind of consideration to other party, right? So this could be choice of optimization playing role in biasness. And on top of that, most of the time in many of the applications, what we do, the output generated maybe at the training time or at the inference time also, we rank the output, maybe a probability distribution where the more probability is given, and you rank maybe the less probable less in the and down and more probable to the top. Or maybe in IR, information retrieval system, you get the documents which are retrieved, and you have, like, you search a query on the web to the internet, right? And this gives you and this could be Google or Bing or something like that, and then it gives you a ranked list of documents. And if you are doing this ranking algorithm can also involve some sort of it could be non-sensitive to the biasness, could be sensitive to particular, giving emphasis to a particular gender, giving emphasis to a particular region or religion or race and so on, right? So again, ranking of output can also be the place where the biases can be introduced, right? When now the very important stage is evaluation. So why evaluation is super important? Because we have, let's say, data set, and you can call it squared for question answering. You are familiar with the squared, or maybe in vision, people who know computer vision, MNIST data set, right? So MNIST, right? So you might know that this squared or MNIST data sets, these data sets or benchmarks are the driving force behind the novel models, the effective models. So you come up with a model M1, you apply to the squared data set, you get a X performance, you improve the model to M2, you apply to the squared data set, you get X plus 1% accuracy or performance, and you keep on improving it. And that's how these benchmark data sets are the driving force behind novel and effective models. So you can also consider the MNIST for vision kind of task, right? So that's why these benchmarks are super important. And if the biasness is present in the benchmark itself, so this benchmark data set, let's say squared data set, have some sort of gender bias, region bias, or racial bias, what will happen? So it will turn out that you are developing in iterative fashions multiple people. I'm not saying just one team is developing multiple models. The whole community, whole research community is developing models to benchmark their model on squared data set for question answering, and the biasness is present in the benchmark itself. So you're now what you will do, you'll optimize your model for this squared data set to perform better on this squared data set, and indirectly what you are doing, you are trying to fine tune your model. Fine tune in a sense, you'll tune your model, you kind of innovating the model, and with the objective of keeping the bias, right? So bias is already there, so you want to keep it. That's why you will be able to perform on this data set, right? So if the bias is not there, then on this data set you will not be able to perform well, because the bias is present in this data set, right? So that's why the benchmark data set is super important, to have this benchmark data set as neutral as possible, right? So there should not be any biases in the benchmark data set, right? Another avenue of introducing the bias or ignoring the bias, or making your model insensitive to the bias, is choice of metric. So you might be using some sort of metric which is neutral to each of the party when it comes to, let's say, gender or racial race or religion and so on. But you can also have a metric which is kind of a customized metric and very specific and giving importance to a particular party, particular gender, or particular race or religion or region, right? So if that is the case, your choice of metric is flawed in a sense, which can introduce the bias in your model, right? Which is super obvious. Now the last step is deployment. So you have trained, you have collected the training data, you kind of you were super proactive about not having biases in training data. Then in the modeling time also you were super proactive about not to have biases in the modeling time, and evaluation also you were super careful about not to have biases in terms of metric or benchmark data set. But at the deployment also the biases can be added, right? So how it can be added? Deployed in different settings, right? So let's say a model, it's trained in USA, and this could be a chat model, right? So, and because it is intended, this model is using some data, right? This data most probably and mostly what happens, it will be a Western data, right? So English data, right? Western word data, and it will not be having representative representation of all possible nuances and patterns, let's say related to India, right? So we have different festivals, we have different customs and traditions and whatnot, and different lingos, different slangs and whatnot. So which is not captured in this data, and I trained my model with the Western data, which is intended for USA. Now I want to deploy this model for India, right? So it's a chat model, and an Indian guy start chatting with this model. What will happen? It will face problem. It will be unsatisfied. He will be unsatisfied because they won't be catering to, or it will be insensitive to the kind of nuances, patterns which are related to India, right? So it's kind of agnostic to your customs, your traditions, and your festival seasons and so on, right? So that's why if you are deploying the model in entirely different setting altogether, which was not intended, then that's a bad idea. Then you will have biases, right? So model is anyway biased because it's out of place, right? And change of human perception due to GUI. So let's say all these factors which are not there, right? So you have the model trained with the suitable data, you are deploying in a region which is suitable for this data and the model. What else can happen? You have a GUI, graphical user interface, which is maybe weird, and you are giving output in a very weird way, which can change the perception of the user. It can get the negative vibes from your GUI, which can also be resulted in kind of a biasness towards, right? So maybe some of the GUI which is maybe disliked by black people versus white people in USA. So next set of things what we want to discuss is metrics for bias evaluation, which is super important, right? So what we want to discuss now is how to deal with biases, and what are the techniques or methods which are prevalent when it comes to debiasing, right, your models, specifically LLMs, right? And before going there, before discussing about the techniques or methods, we need to know what are the metrics which you can evaluate, which will give you idea how much bias is there. So as the simple rule is there, the things which you cannot measure, you cannot control. So only things which you can measure, you can control. So if I cannot measure something, I cannot control it, right? Because I don't know what is happening there. So if I'm able to measure something, let's say I'm in the car, I'm going to New Delhi from Hyderabad, and if I'm not able to measure how much distance I've already covered, how will I get to know that? And I need to also get there at some particular time, right? So I need to meet a deadline. And I don't know where I am currently, so I'm not able to measure how much distance I've already traveled. In that case, how I can speed up my car or how can I accelerate, right? So I won't be able to, because I'm not able to measure, right? Similarly, if I want to debias the LLM or models, I should be able to know what is in what amount the biasness is present, right, in my model, right? So now we discuss about the embedding based metrics. So there are three kind of metrics. One is embedding based, another is the second is probability based metrics, and generated text based metrics, right? So when it comes to embedding based metrics, as the name suggests, we need to work on vectors of where the words are represented in terms of vectors, or could be sentences also, right? So at the sentence level. So we have a word embedding in the embedding space, and we can have a sentence embedding. So there could be two things: either you have a word embedding at the word level or sentence embedding at the sentence level, right? And what you need to do, you need to compute the distance in the embedding space. So given two words, which is neutral versus a biased word, we need to compute the distance, and that computation, let's say cosine similarity, will give you kind of a measure how much bias might be there, right? And then at the sentence level also, the sentence embedding, you need to compute the cosine similarity, right? So that's the kind of very superficial level of definition of embedding based metrics. We'll be discussing this in detail also. Now comes the probability based metrics, where we will compute some sort of probability, and we'll see with one example what do we mean by that. And we'll compute the probability for a mask token. So you know MLM, right? So when we were discussing about BERT, we had seen this masked language model, right? What do we mean by that? So for each sentence, we were, let's say, this particular sentence, we were masking some of the words randomly, right? 15% of the words, to be specific. So 15% of the words in whole text corpora, we were masked, and then we were predicting those words, right? So similarly, let's say a mask token is there, and then we compute the probability distribution on top of the vocab, right? So whole vocab, and let's say this word got selected, right? So then this word will fill this. So what is the probability of this? So given this, we'll compute the probability, and we'll compare the fill in the blank probabilities. We'll compare the probability of this versus that, right? And we will discuss this in detail with an example. And then pseudo likelihood, where we compare the likelihoods between the sentence at the sentence level, right? So it is at the word level, at the token level, and this is at the sentence level. Then the generated text-based metrics is the last third kind of metrics, where we have kind of a distribution of co-occurrences. So given two words, what is the distribution when it comes to co-occurrence of these two words, right? So we compare the distribution of co-occurrences in this. And some of the techniques, what they use a classifier. So they learn a classifier, an auxiliary additional classifier, which will tell to the model how much score is there. So this classifier will give the score, right? Other method is compare each word in the output to a pre-compiled lexicon. So we have a list of words which are already compiled, maybe humanly curated, and then we predict our next word prediction is there, let's say, we predict in autoregressive fashion text is generated and next word is predicted and generated, then we'll compare this with a pre-compiled lexicon, whether it's from the lexicon or not, whether it's a biased word or not, right? So depending on that, we'll be giving a score, right? So now in detail we can discuss. So what do we do with this kind of the first set of metric kind? It's embedding based metric and specifically word embedding. What do we do with this? So what we do, we have, let's say, this sentence, this is a doctor, and we encoded it. We get the representation of the doctor, we got the representation of the nurse, we have the representation of a man, we have the representation of woman. Let's say we want to debias it for gender debiasing, right? So we need to debias for a gender specific thing. So for a doctor, we need to kind of tune it in a way that the cosine similarity or the distance between man and doctor and the woman and doctor should be the same, and nurse and man and woman and man should be the same. Nurse and man and nurse and woman should be the same, right? So this is what we want to do. But the problem here, what can arise, these relationship what it's learning, it will be inconsistent with the downstream task. So you will be able to debias here, let's say, but when you do downstream tasks, these debiased word embeddings will not hold. So this debiasing will not hold when it comes to downstream tasks. So when you do, let's say, question answering or you do summarization and all, the biasness again kind of comes up, right? So this is one of the problem. Another problem is this cosine distance, what we are computing between the vectors to see whether they are similar, dissimilar, how far they are from one another. It is not sufficiently capture the kind of a biasness concept, right? So biasness property, right? And it might just capture only superficial level of bias. So bias is not super simple. The kind of idea of biasness, let's say gender, man versus woman, it's not super trivial, so that you can just treat it, it will be present in a particular word, and if you just close, you kind of reduce the distance between these two words, it will be solved, right? So just the cosine similarity is not a good measure to compute the distance between two words when it comes to biasness, right? So this is what the idea here. So these are the drawbacks. So the next method what we wanted to discuss is probability based methods. And what do we do here? So with an example we can see. So for mask token kind of methods, what do they do? We have a sentence, C is good at, and then we mask one of the word. Then we feed it to the LLM, and model needs to predict this mask word, right? So similar to MLM, right? So mask language modeling. When it predicting, what it will do, it will create this probability distribution, and how much probability will be there? Let's say vocab size is 1000, then 1000 probabilities will be there, right? And let's say you got this art, math and whatnot, and art is having more probability, versus if you put he is good at mask and you compute the probability, the math is more. So you can see the probability of art is more in case of women, and probability of math is more in case of men. So it's biased, right? So what you need to do here, you need to see this, you can compute this with how much probability is given by art to the woman, and how much probability is given by math to the men, also vice versa, how much probability is given to the math to the woman and art to the men, right? So based on that you compute it and you get a score. On top of that, the next method is which can work, it's a kind of pseudo log likelihood. So what does it mean is, women are so bossy, and you kind of give this to the model and it will compute a conditional probability. So given the woman, what is the probability of woman considering the sentence is S1, right? So let's say this is S1 and this is S2. Given the sentence S1, what is the probability of choosing woman? And given the sentence S1, what is the probability of choosing bossy, right? So it's a conditional probability based rule. And similarly for men, given the sentence S2, men are so bossy, what is the probability of choosing men given in sentence as to what is the probability of choosing bossy, and you can see what probabilities are given to this, and based on that you compute the score, right? The problem here is these these probabilities what you get here are not highly correlated with the bias. So their observation is that when you compute this probability, although it's kind of correlates to the biasness, how much greater is the probability in negative sense, let's say women are so bossy versus men are so bossy, right? So not kind of, you're not getting a neutral probability with the same thing. So you're getting more probability, let's say women are bossy, and which is, if you get that thing, even then it turns out that these probabilities are not the they don't reflect the real biasness, right? So they might reflect some, they tend to reflect some sort of flavor of biasness, but it's not a real biasness what they are reflecting. So there is a weak correlation. They found out that there's a weak correlation between the biases and the probabilities, right? So that's why this method is also, this metric is also not super good. On the other hand, the other problem is the mask token metrics rely on templates, right? So you are relying on templates. You are masking this, you are masking this, right? You are not taking care of syntactic and semantic diversity. So you should be able to mask another words also. So templates are less in number and they are static, and they are not, lots of permutations are not there. So this diversity, this representation diversity is not there. If that diversity is not there, you're losing out on some of the biasness. And that's their claim, that if you are relying on templates, then you are losing on some of the biases which are not captured, right? Okay. So next set of metrics, and which is the last set of metrics, which is based on generated text based metrics. So you generate the text and then you do, we compute the score or metrics. So what you do here, it could be a distribution base where, let's say, the engineer should, and now model needs to complete the word. So it's a generation, right? So we need to generate the text, publish his work, go to his lab, develop her skills, right? So engineer is treated as man versus engineer is treated as woman, right? So this is what you need to see. And it turns out that engineer, 2 times it is treated as male and 1 time it is female. So that's why there is a bias. So you can use this to compute a score, right? So how many times male terms is used, how many times female terms is used, right? So it is based on distribution. So it have more possibility of getting male and less possibility of getting female terms. On the other hand, next set of words which use text generation and also is classifier. So you learn auxiliary classifier, this classifier. So let's say C was thought of as, and then you have some kind of a cursing word or abusive word here, right? He was thought of as smart and strong. So you are, anyway you're saying there is a biasness, right? So she was, then you have a cursing word, he was, it's a kind of a good words or positive words. Then you are getting the probabilities here, right? So this classifier says this, it can classify this with the 0.95 score and it can classify with 0.1 score, right? So it turns out that there is a biasness here, and most of the time she was, you will have some abusive word versus man will not have. So this classifier can give you a score which will tell you whether your output is biased or not, and it can also and from that you can figure out how much bias is there, right? So with this classifier. Next set of techniques, they use a lexicon, and for similar for same example, you have a lexicon. Lexicon is just a directory, kind of a list of terms, right? And let's say you have all the negative words or the slangs, all the curse word, abusive words and whatnot. If it is a part, if the generated words, these curse words are the part of this, and let's say these are not the part of it, so no word in the lexicon and more words in the lexicon. So if it is a part of the lexicon, you can see that this model is generating the hate content, generating the abusive content, and it could be for race, could be for gender, could be for region, could be for religion and whatnot, right? So it depends on what kind of lexicon you want to use, and then you can see whether the words are present in the lexicon or not. If no present, then it's good. If it is present, then there is a biasness towards giving this particular gender kind of a negative a term, generating a negative term for this gender, right? So what are the problems which can be there in this kind of these techniques, which are text generation based techniques? So modeling choice can significantly shift the conclusions, right? So how you are modeling this, so what is the input, what is the format of the output and whatnot, is a template based or not, it can significantly change the conclusion. So if the format is changed, if the setup is changed, for the same benchmark, you might get different results altogether, right? So that's why it's not consistent across all the data sets. For benchmark, you need to have a uniform choice of modeling, right? Then the second problem is impact of decoding parameter choices. So here, let's say the generation is there, and we have covered NLG, natural language generation. The decoding parameter could be beam size, could be temperature value, could be some of the how do you choose greedy versus non-greedy approaches, speculative sampling and whatnot. So depending on that also, this will differ, right? So if you're changing the probability, you're making the kind of a skewed distribution into a flattened distribution and whatnot. If you are applying those temperature values, different values, then your scores and then your performance will change, right? So your evaluation will change, right? So it is also have some impact. So you need to cater to or factor in these parameters also. You need to keep these parameters intact or consistent across all the samples and across all the benchmarks, right? Then the classifier based metrics may be unreliable if the classifier itself has own biases. So this is super important thing. If there is a biasness in the classifier itself, then itself it is biased towards, let's say, giving negative thing for gender she, right? So women, then it will generate the kind of thing it will generate will be not correct, right? So this kind of another avenue where the biases can be introduced, right? So if you adding a new module altogether, you are opening a gate for biasness to come, right? So classifier itself is biased, then it will give a poor evaluation of your model. Then lexicon based symmetries may be overly coded. So these terms, they cannot be exhaustive, right? So there are so many slangs, words, curse words and whatnot, and so many dimensions are there. You cannot have a very exhaustive list, and also maybe these words are at the very superficial level. Most of the things, fine-grained things, are omitted. So in that case, it will not be in many of the samples. For those samples which are having out of dictionary, out of vocabulary words, out of lexicon words, you won't be able to kind of get a score, evaluation score for that, right? So that's another problem with lexicon-based metrics.